So hello everyone, welcome back to our Toronto AI in Robotics L seminar. Today we are glad to have Dr. Hadi Sadati to give a talk on reinventing catheters by soft robotics, thrombectomy for acute stroke. Dr. Hadi Sadati is a CME research fellow at the School of Biomedical Engineering and Imaging Science, King's College London, UK. He was a PhD in soft robotics from King's College London, a Master of Science and Bachelor of Science in Mechanical Engineering from Sharif and Amir Kabir University of Technology. He has been a postdoc in continuum medical robotics at King's and in morphological computation at the University of Bristol. He was also a visiting researcher at LASA EPFL Soft Robotics Lab, ETH, at the Professor Walker's Lab, Clemson University, and Dyson School, Imperial College London. His research interests are soft medical robotics, embodied intelligence, system dynamics, and mechatronics. So yeah, Hadi, we're all looking forward to your talk. The stage is yours.
Yeah, thank you so much. Okay, let me start by telling this. What I'm going to present is kind of the theme for the lab that I'm pitching for in all of my applications these days. So I wanted to spread the name of that thing. Also, it's not happening yet. So this is Hadi Sadati. I'm a CME research fellow at King's College London, Department of Surgical and Interventional Engineering. I'm at Arvin Lab with Christos Bergles. I'm pitching for SARE Lab, my own one, soft intelligent robots, and my vision is medical interventions, industrial inspection, and human augmentation via intelligent robots. Let me give you a motivation example, which is going to be the topic of this this seminar. Acute stroke. It's the 4th cause of death in the UK. Costs 1.7 billion on NHS. And we have a short time frame to act for reasonable results, say 2 to 6 hours, and the outcome degrades as we postpone the intervention. The actual intervention in this case is thrombectomy, which is basically mechanically using catheters to remove the blood clot. But there are limited facilities across the UK, 78. And as a result, only 17% of eligible patients received this treatment in 2019, a very low number. Now imagine we can have a body fixed actuation unit, so reduce the need for highly equipped facilities that can deploy an incision growing robot for safe navigation through the growing tissue to reach the blood vessels. That has a steerable tip, so you can navigate the blood vessels all the way to the brain, where it can interact with the blood clot or any other complication present with its multi-purpose toolset. Now imagine if we can achieve this by inspiration based on how guinea worm travels our body. This worm resides in our body for a year, travels all the way from the stomach to the lower limbs without any damage to the organs. And that's my vision for the future of continuum robots inside human body. This is a very fascinating topic of research for many funders, and of course requires a lab that works on bioinspiration, automation theory, and prototyping. A bit about me. This is kind of an overview of what I did. Well, thanks to Wu, you already know that. Started in Iran, then I joined King's, visited Imperial and Clemson along the way, and have been a postdoc at Bristol, King's College, during which I visited APFL, ETH, and more recently as a part-time researcher at QMUL as well. Some publications. On the other hand, I've been active in, with community services in soft robotics community since 2014, we're publishing newsletters, soft robotics debates, etc. So I invite you to follow our newsletter. Also get in touch if you're interested in supporting us anyway. But let's back to the case of acute stroke. So we have 6 million strokes. This is the second cause of death worldwide, fourth in the UK. And this is the third disability cause. Basically, 2/3 of the survivors suffer from some sort of disability. But we have only 24 centers across the UK and 78 experts who can perform this specific procedure, basically unblocking the blood clot with catheters. And these centers and experts are concentrated in a few large cities, so disproportionately placed across the whole country. The current robotic systems that I'm going to talk about them a bit in the next slide, they mostly suffer from minimal automation, and also they're mostly focused on other vascular interventions, and not a specific and less research has been done looking into acute stroke, blockage of the brain blood vessels. Other shortcomings are still highly trained experts and equipped facilities are required. We need an on-site stroke service in case a bleeding happens that may lead to death. Minimal sensing, haptic feedback, and autonomy present. And also usually passive guide wires are being used, and also single tools can be deployed via those robots. In the project that we proposed, we had these research goals in mind. Safety, so we want bleeding-free incision, and we want to reduce the blood vessel irritation, vasospasm, perforation, and aneurysm rupture. So these are the common side effects of catheter interventions in general. The second goal is efficacy and precision. The idea is we achieve higher steerability of these catheters via stiffness and orientation control, and perform autonomous navigation via force sensing and fluoroscopy imaging. And finally, delivering the task, thrombectomy, removing the target blood clot, or perform the required treatment for aneurysms or stent placement, as well as being able to perform drug delivery where needed. So this whole project was proposed as a part of my CME research fellow a year and a half ago. During this research fellow, I was supposed to put together the preliminaries for this proposal and proof of concept. So we proceed with larger fundings at the end. We've been to unsuccessful trials so far, but we are going for another one sometime soon. So what I'm going to present today is basically the preliminaries that and the background that came together to have this specific proposal in place. Before I jump into the different workspaces of this project and tasks, let me show you what's the standard robotic setups in action in hospitals, not in research. So here we have Siemens CorPath. They use a cassette to pass a single guide wire through, and then they navigate the guide wire through the blood vessels via semi-automation framework that they have to reach the intervention site. This is mostly focused on heart-related disease, but this CorPath is the only setup that we have patient results for thrombectomy, basically surgery inside the brain for. Other setups, no one has tried them for acute stroke in brain. The second one is Hansen Medical Module 1. they're dissolved now, and they're not looking into neurovascular interventions anymore. But their setup had a tendon-driven catheter for reaching the heart for ablations and other interventions needed there. And a most recent one is Niobe system, which relies on magnets that steer a magnetic catheter through the blood vessels all the way to the intervention site. This is industrial versions of, or deployed, clinically deployed versions of the robot. During the rest of the talk, I kind of pinpoint the academic versions in practice. But now you know about the whole project, it's good to jump into this specific parts. First is the body fixed actuation unit. The actuation units at the moment in action are cassette-based design. Why they're called cassettes? Because a single guide wire is placed between rollers, and those rollers, like an old multimedia cassette that you use in Walkmans or etc., to basically push forward and backward the guide wire. The issue is implementing the rotation is not that easy. So other solutions like frictional-based rollers are introduced to achieve both rotation and incision of the guide wires. Limitations are, this is only limited to a single guide wire, and usually the guide wire is not off the shelf. You should buy them from the company themselves. A standard version in academia is, again, rollers that you put them in series, as you can see here, for example, in this work by Kim et al. From MIT. But the issue that you have there is, again, you only can roll but not twist. Of course, they didn't need it because they had magnetic navigation here, magnetic steering here. But another issue is the large distance between the rollers may cause the catheter to bend sidewise during the procedure. A more recent design is pinch and push designs that basically similar to human hand. They pinch part of the catheter, push it forward, and then retract, do the same thing again. In theory, they can push forward a catheter with infinite length, but again, deploying rotational degree of freedom is an issue. Putting multiple of these in series again causes side buckling of these very thin catheters, depending on the distance between these units. What I proposed is, based on our work at Arvin Lab on age-related macular degeneration, based on concentric tube robots. So we had basically pretty good setups at our lab. A large concentric tube robot, as you see here, for our dynamic and modeling, dynamic simulations, modeling and control studies, and a smaller version, as you can see here, with a replaceable tool set that we could put at the end of a Kuka arm to perform drug delivery inside an eye. These are done by the previous, by the current and previous postdocs and PhD students at our lab, fantastic people. But when I started, basically the pandemic hit, so I wanted to put this picture here. It's messy, but it's basically my setup on in our coffee table on our coffee table at our house during the pandemic. And this has a structure pretty much similar to one of CDRs that, well, Jessica, you have at your lab. It's basically three linear actuation units with three hollow shaft rotational actuation units, and you can steer three concentric tubes all together. You kind of see them in action here. I like to call this setup an affordable one because it only costed us about 400 pounds, like maybe $500 or something. I took it to EPFL during a research visit, and it is at the moment at University College London for another collaboration. So the benefit was basically being affordable and being able to move it around for different purposes. I basically made a larger version of that. Of course, this would not be a medical or clinical version of the robot, but it has some advantages that I'm going to talk about. I have 3 actuation units on a single linear screw for linear motion of the catheters, and 3 hollow shaft rotational units for rotating these catheters. On this setup, I have a catheter, a microcatheter, and a guide wire, and I can control that via a PlayStation joystick. The parts that I covered are the design that prevents the setup the catheters from lateral buckling. We are putting a patent, filing a patent for this, so I cannot show that, but I briefly can show how the whole thing moves. The motion is kind of a stepwise because I have stepper motors here and CNC control boards controlling the whole thing via G codes. So we have some stepwise motion, but the good thing is, unlike other designs, we have a ready-to-use version for our navigation, modeling, and basically research purposes at all, without the limitation of not being able to have more than 1 catheter or not being able to rotate the catheters during the procedure. Okay, of course, it's not a body fixed actuation unit, but that was kind of the proof of concept of what we want it to look like, kind of, and also it gives us the platform for our further tests. Second part of this proposal is a robotic incision based on soft growing robots. So for those of you who don't know what a growing robot is, this is basically an everted plastic sheet, which is everted outside to inside, and it can by pressurizing this sheet, it basically everts out. So the part that's inside, it everts out. Why we call it growing? Because the part that's deployed in the environment remains stationary, and we have kind of additional material at the tip of the robot. So it's kind of like growing. The benefit is you don't need to push it against the environment. It remains stationary in place, so you don't have friction issues. Inside the body, you don't get all of the issues related by pushing needles through the tissue or things like that, because it stays in place. Also, as you can see in this video, it can go through very small openings. So you can actually have a small incision port, then expand it without the need to tear apart the tissue by just compressing it. We had a postdoc at our lab working on something similar in miniature scale for mammography, and our publication was the first miniature growing robot at the time, and it got published. What you see here is the tiny growing robot with its steerable catheter at the center here, a large fluidic tank to provide the growing pressure, and an active channel to pass through the catheter or the drugs that we want to use during the procedure. This is kind of the robot in action. Being miniature, we had a lot of issues for effective growing of the robot. So you see the inner catheter, which is a tendon-driven catheter, needs to push in and out to promotes the growth of the sheath. But overall, we have effective growth and steering. Fantastic job by Pierre. He has a company in France at the moment pursuing the same idea, but we have talented PhD student visitors at our lab continuing the same research. So in a recent work, so apology for the very rough drawing, but in a recent work, we tried to do inverse kinematics and also inverse mechanics based on principle of virtual work for this type of robot. On the inverse kinematics, we just related the radius of the curvature based on constant curvature assumption to the length of the tendon inside, and then could relate the length to the radius of the curvature. We know from by knowing the length and radius of curvature and constant curvature kinematics, we can know the tip of the position of the tip of the robot. So this is basically the inverse actuation, the inverse kinematics for the actuators. And here LT is basically the length of the tendon that we need to pull to get the desired radius. But as I'm going to show in the next few plots, we needed to improve this to include the mechanics of the system in place. Mechanics include the pressure inside the growing sheath, the tension in the tendon, and the bending of the catheter. Using principle of virtual work, we could calculate the energies, and then by just calculating the partial derivatives, we could get a more precise relation for the radius as a function of the length of the tendon, and the inverse map for that. Okay, the plots that I'm going to show are the work by a talented PhD student that we have, Zikong Wu. So I encourage you to stay tuned with the results out of his work. So you kind of in this plot, you see in red the experimental data, and in green the results for the mechanics based on principle of virtual work, and in blue the inverse kinematics without considering the mechanics. And you see how considering the mechanics how much it can improve the accuracy of the model compared to going for the pure kinematics. He did a nice job. Zikong did a nice job in verifying the accuracy of these models, and put a PID controller on top to achieve trajectory tracking. This paper is under preparation for RoboSoft. So again, I encourage you to stay tuned with the results in that. On another work, we looked into finite element modeling of these growing robots in SOFA. So we modeled the sheath as a set of spring dampers that can collapse. So we can model the eversion of the sheath, and a set of spheres to model the collisions arranged on the edges of a square. So we can actually control we can stably get a growing of the sheath on top of the steerable catheter that we have. You see instances of this growing here, and kind of instances of the growing in our actual system, and the results of our verification studies. You can see for the bending of the catheter under tendon tension, we can get the simulations pretty good. And also for the effect of pressure on the growing speed of the robot. Although there are errors, but we can get pretty close results from the finite element simulations and the actual system. But the miniature system design posed a lot of issues in our verifications. We have this paper under review, so I encourage you to again to stay tuned for that one to come out. Here you see the result of the effect of pressure on the stiffness of the growing sheath under gravity, and you see as the internal pressure increases, the stiffness increases, so the system becomes more straight. Again, we have good accuracy between experiments and simulations. And here you see the effective, the pressure and the stiffness of the system when we have the tendon-driven catheter inside. The result, the outcome is pretty minimal. So increased pressure results in a stiffer system that tries to bring the system to the straight configuration. Again, we have good accuracy between our models and our experiments, but it's not that obvious on the actual system. Finally, we just showcased. Well, it shouldn't play in full screen, but it doesn't matter. We showcased cases with complex interactions of the robot with the scene. And in this video, you see the steerable catheter in red and the growing sheath in yellow. This is actually the first realistic, or let's say high fidelity model of a sheath during eversion growing. All the other models in the literature, they simply have simplifying assumptions for capturing this change of length in the system. And this is another simulation for interaction of that specific robot with mammary ducts based on SOFA framework. Okay, so that was actually you have a talented visitor to work on the implementation of these growing robots for incision inside tissue. So again, stay tuned for the results on that. But let me go to the next part of the project, a steerable tip for these catheters. Again, I want to back to our work on age-related macular degeneration with concentric tube robots at our lab. At our lab, we used these needle-sized concentric tube robots. I was mostly in charge of the modeling, but we had a good work from a previous PhD student on planning and reachability study of the whole work, and also current PhD student who did a fantastic job with putting virtual reality environments together for the whole thing. But okay, how steering a catheter would match or relate to a concentric tube robot? The idea is the catheter, the combination of the catheter and guide wires, they're already concentric tube robots, and surgeons are actually bending the tip of them based on the task that they want to do. So unintentionally, they're actually using these systems as a concentric tube robot. We had earlier work, another PhD student who I collaborated with on micro concentric tube robots for going around the eye and performing optic nerve sheath fenestration. So we thought, why not having tiny concentric tube robots at the tip of the catheters, or use the off-the-shelf catheters, pre-bend them, and just use our knowledge of concentric tube robots to control these systems. Okay, this part of the project is also under ongoing. So I'm not gonna present you specific results on that, but I'm going to present you the background regarding the control, the modeling and control of these concentric tube robots. So this is the concentric tube robot that this is the concentric tube robot that we have at our lab for our simulation and control studies. For those of you who don't know what a concentric tube robot is, we have pre-curved individual tubes. By putting them inside each other and rotating and sliding them with respect to each other, we can get complex 3D shapes. As a result, we can act as a steerable needle. For modeling them, we need to consider the twist along the backbone of these robots, but shear is not that important, or elongation. So it's only mainly the twist between the tubes, the effect of the tubes on each other, the boundary conditions, and also the sliding of the tubes. To model them, I want to actually go deep a bit about how a continuum robot model should put in together. Usually in the literature, you see continuum robots are modeled based on constant curvature, piecewise constant curvature, modal approach, finite element methods, etc. But we can actually break down the elements of a continuum robot model. We can break down that into system kinematics, system mechanics, basically governing equations, and material mechanics or constitutional law. And then we can approach the solution for that. System kinematics is basically the relation between the task space or the workspace and the actuation space. The system mechanics is the relation between inertia and forces to that kinematics that we took into account. And material mechanics is basically, if we assume like Hooke's law, hyperelasticity, viscoelasticity, things like this into account. I invite you to have a look at our previous work on how we can break down the research in the continuum robot community into these different categories, and how we can combine these different methods to come up with methods that sit in between what we've already seen in the community. A bit about kinematics before I jump into our specific way of modeling concentric tube robots. We have differential kinematics, which is variable curvature kinematics based on Kossarov rod. We can discretize it and have it as a pseudo-rigid link robot, basically a highly articulated series rigid link robot. Or we can have Euler-Bernoulli beams in between these discretized segments. So instead of having a rigid segment, now we have a deformable one. And for that Euler-Bernoulli beam representation, we can say our states are the bending and elongation of those Euler-Bernoulli beams, or our states are the actual position and orientation of a few points where those Euler-Bernoulli beams are connected to. So we end up with relative states or absolute states. These are discretized models. We can approach a continuous model, which is called the modal approach. Well, I like to call it reduced order modeling approach, but the community knows it better as modal approach. In a modal approach, you assume the backbone shape to have a specific representation. It's very similar to interpolation or curve fitting with polynomials or splines or things like that. So a way of doing that is having these splines or polynomials as the shape of the robot, so that gives you the kinematics of the system. Then you can mix it with any conservative law or constitutional law later. But for concentric tube robots, we identified that having a separate representation for position and orientation does not guarantee tangencity of the local frames. So we improve that a step forward to the case of Bishop's frame. So now we have a correction twist on top of a tangent frame defined based on the shape of the robot. Resulted in more complex derivations, but improving the accuracy in terms of that constraint. There are other works that assume a polynomial or a spline representation of the curvature and a strain instead of the shape itself. So as a result, parameterizing the curve using relative states or using series link, because it gives you relative states, they're similar, and finite element approach by assuming the states to be absolute, or using modal representation for the shape itself, they're kind of similar because they're talking about absolute states. That's the kinematics. On the dynamics, I like to use TMT method. So it is a bit different from Lagrangian method, but you can drive it based on principle of virtual work. We basically can say have a summation over the inertial term, Coriolis term, and conservative and non-conservative terms on the system. And since it's a summation, it's really easy to add a new element or remove an element from the system. It's basically adding the whole the equations for that specific element into this summation. Here, it is called TMT because the representation of the projected mass matrix in the coordinates frame, and we can derive V based on this. We proposed a continuous form for that based on integration of differential masses and Coriolis terms and conservative, non-conservative forces along the backbone of a robot, and also suggested the inverse mechanics or inverse dynamics for the system to design a Jacobian-based controller. But why using TMT method instead of a Lagrangian method? In this graph, I kind of show if you want to start from a system kinematics and end up with a closed form for the system equation of motion, following Lagrangian method, you need to calculate the Lagrangian, calculate the partial derivatives, then time derivatives, and start collecting coefficients of accelerations to end up with this closed form that we need to work with to design a control. On a TMT method, you basically calculate all of these elements straight away in a single go. And then, yeah, you have a second step of derivation, but there is no step involving collection of coefficients. So it's actually very efficient if you want to automate the derivation of the equation of motion for the system, and it involves less steps. Also, as I said, it's really simple to remove or add a new element to the whole system. So that was actually that was the backbone of my open source package TMT Dyne that a while ago I used to compare the performance of different kinematics assumptions for modeling a stiff flop module experiencing external force. A stiff flop module is basically a silicon soft appendage with 3 pairs of pneumatic braided actuation chambers, and upon actuation of these braided chambers, part of the appendage elongates, so it bends sidewise. Also, it could elongate and on demand by pressurizing all the segments. You see, we tested cases with extensive external force, bringing the system to the S shape to really verify the performance of the system. And well, I don't want to spend too much time on this, but a comparison between the derivation complexity, we noticed that using Euler-Bernoulli beams with absolute states, it's the least complex, and using a serial, basically pseudo-rigid body approach is the worst if you have high number of 3D links. And using a model approach or reducer model is it sits somewhere in between. Then we provided plots on the simulation time and absolute error in predicting the tip position of the system for a static no load case and dynamic no load case, and also a static with load case and a static dynamic with load case. Again, if I would just want to summarize what you see here, a model approach provides the most accurate and less sensitive, but computationally expensive for high orders model. An Euler-Bernoulli model with absolute state, basically a discretized model, if you assume Euler-Bernoulli beams with absolute states, which is very similar to the finite elements kinematics. It provides the most computationally efficient model with good accuracy, and it's good for if you have a large system. But series rigid link model, basically pseudo rigid body approach, it's the most sensitive if you take into account hyperelasticity assumptions there. And also it tends to be pretty slow compared to the others. So looking at these two, you either need to go for finite element or model approach. So for our concentric tube robot, we took the model approach because we wanted to model the sliding of the material, the dynamics of the material that's being translated along the robot. How did we do this? We assumed a general backbone shape, and then for different tubes, we assumed boundaries that we basically integrate over this general backbone. Since the whole system gonna take one shape, a unified shape. So this general backbone is common between all the tubes, but since the tubes are moving along the robot or this general shape, the integration range for the continuum material of that tube should be updated based on the motion of the system. Also, as I said, we introduced this the bishop frame format for capturing the local frame based on a tangent frame to the backbone shape plus a correction twist on top of that. Okay, using TMT-Dyne, all of these features, and we integrated them in TMT-Dyne, and this is the kind of interface that we use to model the whole system. The good thing is we could capture different types of translation of elements along a single backbone. Later on, I'm going to show you how we use it for modeling growing robots. Okay, see that I'm short in time, so I probably proceed a bit faster. But here you see some of our comparison between our simulation and experiments. We presented the second dynamic model for concentric tube robots in the community, and our model was unified. So you don't need to switch between different models to capture the snapping and non-snapping conditions. Also, the overall accuracy of the model remained around 6% for the combination of snapping and non-snapping situations. As you can see, we had a complex case with multiple instances of snapping between the tube to get this tested. So in that sense, I can say that I'm proud of this work. Other than that, we didn't consider the friction, but we considered the viscous damping, nonlinear viscous damping, and that was enough for us to capture the asymmetry in the motion of these a concentric tube robot. So basically, if you rotate the tubes clockwise and it snaps during that motion, if you start counterclockwise rotation of the same tube undergoing another instance of snapping, the forward and return motion, they don't coincide, so they don't overlap. That there's a shift between the plots that you cannot capture that with static models. But in this dynamic model, we could kind of successfully capture that, as you see in this part of the plot. Error results, large errors during the snapping instances. On the left side, you see simple translation. On the right side, you see cases with snapping. Again, you see the asymmetry between the forward and return motion that we could capture, and large errors during the snapping, relatively large errors after snapping, but overall the error was within 6%. And also you see that we could capture the simulation result, the solid lines pretty much coincide with the dotted ones, the experimental ones in our unified dynamic case. We also had a case of, we also presented a model based on SOFA framework, based on their beam plugin to model interaction of concentric tube robots with the deformable organs, and compared it with our dynamic simulation. As you see, the blue solid lines, they kind of correlate with the experimental results, but they cannot capture snapping. So we concluded that the current implementation of the beam plugin in SOFA is not adequate for capturing instability in a slender continuum rods. And as I mentioned, sorry for the noise, now we could model addition of the material to the tip of a system, not just a sliding of the element. So we modeled the dynamics. We presented the first 3D dynamic model of a growing robot that can capture the translation of the material, basically the inner and the addition of the material to the tip, which is still an interesting case in the community. Again, comparison of the experimental result and simulation results showed good accuracy. Well, of course, we need to verify this in 3D simulations with longer growing robots as well. Okay, I probably just quickly go over the last part in a few minutes. I skipped the autonomous navigation, of course. This part is ongoing, but I didn't have much to present on that. But I want to jump to in the multi-purpose tooltip, which is basically a gripper-equipped needle with force sensing. So basically, we have force sensing. Also, we have a needle for drug delivery, but also we have a gripper there that grips the target tissue for the needle. So the standard tools being used for thrombectomy and clot removals are basically using suction to remove the blood clot, using Kelly guide wires to drill through the cloth and then suck the debris, or a better solution probably using a combination of blocking the blood vessel and collecting the blood cloth so the residue doesn't propagate through the rest of the blood vessels, blocking the smaller veins further forward. So we didn't focus really on how we're going to capture the blood clot because there are a lot of good tools there. We focused on how we can sensorize it and also how we can have better, how we can achieve drug delivery. Because if you can navigate the blood vessels, you basically have access to a lot of places inside the body. And if you can have targeted the drug delivery through incisions with needles, that would be really beneficial. What we proposed was a needle that pierces through a jelly suction cup. The suction cup and the needle are isolated through a T-joint, so the needle can be used for drug delivery, and the suction cup can still perform as a means of grasping the tissue. We noted that you see how small the size are, and we deployed that at the tip of a concentric tube robot because, well, it is already concentric tube structure with a needle at the center and another tube around to induce the gripping suction. And you see it is a small design. This is designed for optic nerve fenestration, going around the eye orbit and performing drug delivery behind the eye. But of course, we hope to miniaturize it and make it softer to deploy through catheters for catheteric interventions as well. Okay, but before I proceed, I want to say a suction cup wasn't good enough. So we noted that we need to have a sticky suction cup to improve the grasping. So the suction and stickiness helps grasping the tissue, but then for releasing the tissue, we needed to actually puff out air to release the tissue. We did some finite element analysis based on an axially symmetric model of the suction cup. The block on the top is the cup itself. The deformed part is the gel of the suction cup, and then we have the subtrace. We had cases of push sealing the suction cup at the initial when we want to grasp the tissue, initiating the pull when we pull the tissue up, and then near grip loss when the force of the tissue is large enough to release the grip. and compared it for dry surface and wet surface, and also different sizes of the gel, and also the effect of grasping a soft surface. Again, with different with gels with different dimensions. In short, we noted that having a cup 10 times softer than the tissue helps with better grasping of the tissue, and also a grasp is better on a wet surface because of the smoother expansion of the gel. But also on a wet surface, we got reduction in the effective suction area. So it pointed out that the suction cup need to have a cone shape, a structure, not a cylindrical one. We did, in an earlier work, we did the tests on the force required to penetrate optic nerve with a needle, and also the threshold that the optic nerve sheath is penetrated, but not the nerve itself, because we don't want to damage the nerve itself. And we noted that we need 0.1 Newton force to achieve the sheath fenestration, but not damaging the nerve itself. This is the early work by Zeus's Mitros, showing the miniature concentric tube robots can achieve actually this task when we move them, we push them around the eye orbit. Okay, back to the suction cup.
Hadi, may I quickly? We only have 4 minutes left. We would probably, a lot of us would love to ask you some questions. Could you wrap up your talk?
Yes. So we did accessibility test. We did some test on grasping actual tissues. We couldn't perform incision on the actual tissue. Then we designed a curved cup, inclined one, and did some tricks, and we could achieve 100% incision this time after redesign of the cup. Also, we're working on miniature force sensors to deploy at the tip of the system. You kind of see them in our in vitro test with realistic electrical properties, similar to blood inside our body. But yeah, that's it about the preliminaries that I put together in the past year and a half for putting a larger grant on this one. This is the overall thing that I'm proposing as a part of this grant, and this is the guys, facilities, and universities they collaborated with during this time. Thank you so much for your attention. Sorry it went over time.
Thank you, Hadi, for this great talk. And now it's our Q&A section. Any questions from the audience? You can just unmute yourself and ask the questions.
I'm going to break the silence. Thank you, Hadi, so much for compiling all your research work. I'm familiar with your work, but even today, I learned about a few new things. So thank you for showing us this broad spectrum of things you've been working on or have been involved with. This has been quite cool. I guess I have a more general question about what your take is on what's the importance of accurate modeling of continuum robots, and probably in particular micro-scale continuum robots over, I guess, online state estimation and control. What's the importance of an accurate model?
To be honest, if you have a camera, probably a human in the loop can bring the robot where you want it, and then a simple PID can achieve a lot of automation tasks that you may imagine without a model. So as long as you can just detect where you want to keep the tip of your robot. But then when you want to know about the forces, or when you don't have high frequency, high frame rate imaging in place, maybe because it's fluoroscopy and it's dangerous, then these models can be helpful to give a better estimate to the surgeons. Also, you want to provide information to surgeons regarding the risks associated with a certain action, or alarm them if a certain action results in accumulation of light torsion in the system, and then sudden release of that causes a rupture, things like that. Again, modeling matters. But how much a theoretical model matters there? I should say you need these accurate theoretical models to train a learning method. And through that learning, or data-driven or AI, combine the ex vivo and in vivo and user-specific data. So a theoretical model on its own cannot address those issues as well, but it provides a very good backbone for providing a large data set for you, and also provide the robustness of your AI method or data-driven method, because they're not on their own robust enough, maybe. And then through that AI interface, you probably can achieve the tasks that I mentioned, basically force estimation, providing suggestions, providing risk analysis, etc. So that's my intake.
Mm-hmm. Thank you for your thoughts on this. I have one more specific question. You were showing us the results of your dynamics MATLAB implementation for the concentric tubes, and we saw some snapping in the videos you have been showing, and then the corresponding model, I guess, below. Yeah, right here.
Yeah.
Maybe you can play the videos one more time, because I had difficulties understanding. So is the dynamics model able to predict the snapping motion that we observe in the videos, or are these like synced?
So the videos are not synced, but let me actually show you here. Mm-hmm. So you see actually a slide. So these are the instances of the snapping. Okay, we had we needed to kind of have artificial damping during the snapping to guarantee the simulation convergence and kind of guarantee the real-time performance of the simulation. So although we could predict the start of the instance of snapping, we usually had a slower transition through the snapping as a result. The other thing is that you kind of resulted in being not properly synced here is the backlash in the actuation unit. So we had in this specific robot between 5 to 15 degrees backlash when the motor started to rotate backward, and during the snapping, basically the tubes jump at the end of the backlash. So that was another issue in these. Plus we kind of so partly manually and partly by implementing if else function, we try to overcome that. But again, in the error plots, you see that after snapping we have a bit of larger error compared to before snapping, as you see here, and also a sharp error. So during the snapping it wasn't that accurate. But the goal here is having a seamless and unified framework, being able to capture all of the motion back and forth without a need to switch between the models, as in Caleb's
And I guess
work.
with your comment earlier, you seem to hypothesize that your model can capture hysteresis in the nickel titanium.
We implemented nonlinear damping, but it showed that it can, by tuning the damping, it can capture the hysteresis, but the mechanics of hysteresis is not implemented there.
Oh, I see. Okay,
So
and I guess
realistic.
my last question is, so these are 2-tube concentric tube robots. Would it be possible to add a third tube to that model, and would it still work, or would there need to be additional work?
No, actually, you can, in theory, you can have as many as you want in the framework as well. But it wasn't real time anymore. So I spent some time in a collaboration on how to simplify the dynamics by not considering the Coriolis terms, not necessary Coriolis terms. That part is ongoing. At the moment, the third tube results in a pretty slow simulation.
I see. And I guess on that
but
note,
two
what is
tubes,
the
yeah.
computation time for one cycle for 2 tubes right now?
It really depends on if it's snapping, post-snapping, pre-snapping, but I wish I had the
I guess give me a range.
here.
What's the minimum computation time and the maximum computation time per result?
The minimum, the simulations were twice faster. You know, the worst case, they were twice faster than real experiments. But the best case, they were like 100 times or up to like 500 times faster if it was only like a simple translation.
I see.
Yeah, it's a C implementation, open source already available. Oh, we didn't do any real time, so I cannot claim it's real time. So it's not hard real time, but it has the potential for being real time because it's fast.
Thanks a lot, Hadi. I guess I'm gonna watch out for additions to this work. Thanks a lot.
Yeah, thank you so much.
All right, I have another question. I will just go ahead. Thanks a lot, Hadi, for the great talk. It's very nice. I had one question for your dynamic model of the CTCR in comparison to the model from John Till and Caleb Rucker. So I think you said the advantage of your model that it's more generalized. Can you maybe just elaborate on what you exactly mean by that? I think that would be great.
In Caleb's work, at the instance of a snapping, you need to switch between 2 different solvers. Okay, but in this one, I have a unified solver. It just runs. Okay, and it runs, it gives you results. It just becomes a bit slower during the snapping instances to convert, but it runs. So that's one of the benefits.
And does that result from your? Oh, sorry.
Yeah. The other thing is, so there. Yeah.
Go ahead. No, you go ahead.
Yeah. So Caleb focused on the accuracy of capturing post-snapping vibrations. We didn't care about that, to be honest, here, and we had an overdamped model to go through snapping successfully. So probably his model is better in that regard, but our test case is very much more complex than the cases that they presented in their TRO paper. I want to say that we stopped the system just before another snapping instant. So to see if our model is stable enough and stops there, not perform another snapping. And we went through 4 instances of snapping during each motion, as you see. Yeah.
Okay, and this like more generalized model, does that result from your choice of like a kinematic representation or from your choice of how you do the time integration?
It is, to be honest, I don't know. Yeah, I solve an ODE. Caleb solves a boundary value problem optimization method. So I have a Lagrangian here. He has a Newton, basically a Kossarov rod dynamic there. Yeah. So a lot of things may be in place.
Okay. Well, thanks a lot for answering this question.
Basically, it happened to be good. You know, I did what I've done before, and it happened to be good.
Yeah. No, sounds good. Thank you.
So I have a question. I was wondering, so this kind of application, like medical robotics, is very safety critical, and for the, like this kind of theoretic based control algorithms that are like kinematics based. So is there any, are these algorithms like certifiable? Like, that the deviation from your desired like movement will be no more than some threshold, so that you can apply that to like real human, and that will be safe? Or because you just mentioned like some AI control methods, and I know that for those from all the AI methods, they are not certifiable. Because it's more like a black box, so you never know how much errors it will produce in some real in some new test case. But for the like this kind of methods that have very solid series backbone, will they be certifiable and very safe, or it's still an unsolved problem?
That's actually a good question. You know, I would love seeing reviewers of the papers asking that question, not letting a paper pass without rigorous analysis of the whole workspace, not just by showing a single successful or few successful instances. This is viable. But yeah, but back to your case, yeah, lack of robustness is an issue of data-driven methods. So model-based data-driven methods, they can get the robustness from the physics-based model, and then the accuracy and adaptability from the adaptability to special cases like different patients from the AI part. So that might be a solution to that. The other solution can be designing inherently safe devices that cannot damage, that cannot harm, or that cannot basically kill. Then put whatever you want on top of that. Okay, this is actually a bit unrealistic, but soft robotics kind of gives us the opportunity to look into that. And the good news is, if you prove that your robot doesn't kill, you can straight away test it on human here in the UK. So it's very important to look into this problem from the design perspective as well.
I see. Yeah, that makes sense.
Yeah.
But for the algorithms themselves, is it like for the physics-based methods you just mentioned, they are like have some guarantee for the errors or something?
They are more robust. They are more robust as long as you have known external loading conditions and you consider them properly. They don't diverge, they don't overshoot or things like that, at least in the static case. In the dynamic case, yeah, that simulations may diverge, or you may get lag between the simulation and experimental results. You know, that's you need to dig into the field of robotic automation and all of the matrix for risks analysis and margin of safety, etc. There are a lot of tricks and tweaks that you can put on top of your system, but it is important to verify your system in the workspace of the system, and come up with a cloud map of the risks or the errors in that workspace before putting it in human. Yeah, and in our case, we didn't do that, to be honest. No, in this case, in our simulation, dynamic simulation, we didn't do that. I don't know if my model remains this good in other places of the workspace, but it's not that we did a lot of tests and chose the best one. We basically did a complex test and stick to it with while I was improving my model.
I see. Makes sense. Thank you.
Yeah.
Okay. Any other questions from the audience? If no, I think we can stop here, and let's thank Hadi again for this great talk. And yeah, thanks everyone for coming.